So transition matrices are a bit different from the other matrices we've been looking at, and actually they involve two different matrices that you put together to make something new. So it's used in scenarios where there's going to be change, and that's why we have the name transition matrix. Here's a scenario from your textbook. Ace Ice Cream has 63% of the market for ice cream, other brands have the rest. We can represent this in a state matrix. So we're going to represent this, and the state matrix is going to say that 0.63 are with Ace, and what would the other number be? Oops, I hit a comma. What would the other number be then? If 63% are going with Ace, what percentage would be going with the other?
37.
37, right? So we represent that in the matrix as a decimal. How do you change from a percentage to a decimal?
You divide by 100.
Divide by 100, okay? And the simple way of doing that is to...
Divide by 100.
There is a very simple thing you can do with the decimal point. What is it?
Oh, move it. Two decimal places, right?
Two. Move it 2 decimal places, that's right. So that's what I've done here. I've changed 63% to 0.63, and I've changed that to 0.37. What do you notice if I add together the numbers in the state matrix? What do they add up to? 1. So that means they're accounting for everyone. Okay, they're accounting for what everyone does. 63% are eating Ace ice cream this week, and 37% are eating the other ice cream. It's called a state matrix because it tells us the state of where things are at, okay? That use of the word state. We've given other information though. It says, of those who buy Ace now, 80% will buy again next week. So there's a bit of brand loyalty there. 80% of the people liked the Ace the first week they had it. They're going to buy it again next week. 20% are going to switch to try the other ice cream. Of those who buy other ice cream now, 70% will stick with the other ice cream, and 30% will switch to Ace. So we've got 4 numbers here that we can put into a matrix, and basically what it's saying is that now we've got Ace and other, Ace and other next week. If I was to put this in a table, just to get my thinking organised, right now, out of the people who've got Ace, next week, 80% of them are going to stick with Ace, right? That's what it's saying up here. And 20% are going to change to the other brand. If they're having other now, what number are going to go to Ace? 30% are going to go to Ace, and 70% are going to stick with other. Now just be careful with that, because the words in the question have those numbers around the other way, because it says that 70% are going to stick with Ace, with other. So just make sure that going from other to other is 70%. You've actually got it in the second square there. So that's a table that summarises it. I can then write that in a matrix. And the transition matrix, T equals 0.8, 0.2, 0.3, and 0.7. So that summarises the sorts of changes that are going to happen from one week to the next. Cool with that so far? One thing I forgot to mention up here is this state matrix, we call that S. So S equals that. The other thing I can say about that is that because it's the state that we begin with, we call it SO. That's the initial state. Or S0 is probably better to say. So we're starting with S0, that's where we are to begin with. So the question might ask us, how many people are buying Ace ice cream after 1 week? And so we need to find out what the state will be after 1 week. So after 1 week, S 1 is equal to SO times by the transition matrix. So this is really easy to do on the calculator. You put matrix A will be your state matrix, just a simple 1x2 matrix. Matrix B will be the transition matrix that you've worked out, and then you can times them together and it tells you what they'll be in the next week. And I've got it from here that S1 equals 0.615 and 0.385. Has the number of people eating ACE ice cream increased or decreased? It's decreased, hasn't it? It's gone from 63% of people down to 61.5% of people. So we've seen a bit of a change because of the behaviour of people. They've worked out this is what's going to happen from week to week, and after 1 week, this is where we're at. Okay, this is what's happened. Now, if we want to work out what it is after 2 weeks, S2, we could just get S1 and times it by the transition matrix again. So we could do it in a sort of serial way. We could just kind of work out from week to week what's happening. We could get the result from 1 week, multiply the transition matrix to get the following week, do it again to get the following week, and so on. But that's a bit of an annoying way to try and work stuff out. There is a shortcut. All you need to do, say if you wanted to find how many people buy ACE after 6 weeks. So you're trying to find S6. You can do the initial state multiplied by t to the power of 6. That will tell you what the state's going to be after 6 weeks. So in your calculator, it would just be map A times map B, and you do the hat key, whatever you call it, it's called caret, I think, hat key 6 to put it to the power of 6, or maybe you've got like an exponent, I don't know, whichever button you've got on your calculator to do it. And that will give you the answer. So these answers can all be found in the calculator. It's all really straightforward. Any questions about that? No? Okay. There's one other thing. We can predict what's going to happen over time with this. It decreased in the first week. Maybe it'll decrease in the second week too. Do you think it would decrease all the way down to 0 for ACE?
Perhaps.
Perhaps? No? Why do you think no? Why do you think ACE ice cream is never going to get to 0?
Oh, because people that switch from the other brand will go switch to ACE, which is very insane.
That's right. We know that out of the people who have other brand 1 week, 30% are going to switch to ACE the next week. So even though we've seen a decrease in the amount of people who are eating ACE ice cream, it's not going to bottom out at 0. There's going to be a lower limit where it's not going to get any lower. And we call that the steady state, when things stop changing. To work out the steady state, all we have to do, I'm just going to move that over here, get a blank board. To find the steady state, raise the transition matrix to a high number. So, if I get the matrix T and I put it to the power of 100, transition matrix times transition matrix times transition matrix times transition matrix, eventually what I'll get is a steady state. Eventually what I'll get is 0.6, 0.6, 0.4, 0.4. And when it's steady like that, we know that it's not going to go any further. Well, actually, how do we know it's not going to go any further than that?
Test it out for a week after.
We can test it out for the week after, that's right. We could do T101 and see if we get the same answer. If we get the same answer, there's no more change. Okay, so we know we've definitely reached the steady state. In the book, it suggests doing t to the power of 10 or t to the power of 20. I have found that some of the questions, if you do t to the power of 10 or t to the power of 20, it's actually not quite enough to get to the steady state. So you actually have to go bigger. So I just suggest in a test, if you go t to the power of 100, you're never not going to have it at a steady state by then. If you really want to confirm it though, you can just compare it to the week before, T99, or the week after, T101. And they should give you the same answer. So, the type of questions we have in the book are asking you things like constructing a transition matrix from data to start off with, identifying the meaning of numbers in the transition matrix. So what does it mean in the transition matrix if it says 0.6 in that particular place? It's always about a change of time from now to later. Those units could be weeks, could be months, could be years. You just have to read it from the question as to what that kind of period is.